Hello, my dear students. Welcome to ESR chemistry classes. Here we are in lecture number 8 on ESR spectroscopy applied to inorganic chemistry. In this video, we will discuss G value, the spin energy levels of an electron are separated in an applied magnetic field of strength B by an amount given by the following expression. Delta E is equal to G beta B. This is the energy difference between two spin energy levels of an electron in an external magnetic field of strength B. Here, the term G is called Lande's splitting factor or simply G factor. It may also be called G value. For a free electron, the value of G is 2.0023. The deviation of G from 2.0023 depends on the ability of the applied magnetic field to induce local magnetic field in the free radical. The deviation of value of G from 2.0023 depends on the ability of applied magnetic field to induce local magnetic field in the free radical. The G value is given by this expression. G is equal to GE into 1 minus sigma. Here GE is G factor or G value for free electron, that is 2.0023, and sigma is constant for a molecule which depends upon its electronic configuration. It means the G value depends upon the electronic configuration. Therefore, G value gives an information about the electronic configuration, and thus it is useful in the identification of the species present in the free radical sample. We have already seen that the G value depends upon the electronic configuration, and thus it gives information regarding the electronic configuration of a species, and it is useful in the identification of a species present in the free radical sample. The following facts are noteworthy regarding G value. Many organic radicals have G value close to 2.0026. A number of organic radicals have G value close to 2.0026, which is nothing but the G value of methyl free radical. The inorganic molecules have G value typically in the range 1.9 to 2.1, but the D metal complexes have G value in a wider range from 0 to 4.0. For ionic crystals, the G value is usually in the range 0.2 to 0.8. These four are noteworthy facts regarding the G value of various species. Idea about vector model of atom, which is necessary for the calculation of G value. In an atom, the electron has two types of motion. First, orbital motion. The electrons revolve around the nucleus. It produces orbital angular momentum, and it is represented by resultant orbital angular momentum quantum number L. The electron revolves around the nucleus. It is called orbital motion of electron, and it produces orbital angular momentum. The net resultant orbital angular momentum of a species is denoted by L, which is called resultant orbital angular momentum quantum number, and L is equal to summation of ml values, and ml is nothing but magnetic orbital quantum number. The value of capital L may be 0, 1, 2, 3, 4, etc. And the second motion of electron in an atom is a spin motion. The electrons spin about their axis like a top. It produces a spin angular momentum. It is denoted by resultant spin angular momentum quantum number S, and S is equal to summation of ms values. ms is magnetic spin quantum number of electron. The value of capital S, that is resultant spin angular momentum quantum number, may be 0, half, 1, 3 by 2, 2, 5 by 2, 3, 7 by 2, etc. The total angular momentum of all the electrons in an atom is represented by total inner angular momentum quantum number J. The total angular momentum of all the electrons of an atom is represented by total inner angular momentum quantum number J, which is given by Clebsch-Jordan series. J, the value of J varies from L plus S to L minus S in integral steps. The lowest value of J is selected if the subcell is less than half filled. If the subcell, valence shell subcell, is less than half filled, the lowest value of J is selected for the ground state, while the highest value of J is selected if the subcell is more than half filled. The G value is given by the following relationship. G is equal to 3 by 2 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. G is equal to 3 by 2 plus 3S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. With the help of this expression, the value of G can be calculated. Let us consider different cases arising from the above equation A. For a free electron, there is no orbital motion. Orbital motion is in atom only, not for free electron. And therefore, the value of L will be 0. And the value of J will be S. And therefore, on putting these values of L, S and J in this expression, we get the value of G equal to 2. From this expression, for free electron, the value of G has been calculated to be 2. But the actual experimental value of G for a free electron has been found to be 2.0023. For most of the free radicals, the G value differs only by plus minus 0.003 from this value. There is only slight deviation of G value for most of the free radicals from 2.0023. For ions having L equals to 0, such as Fe triple plus ion, which has electronic configuration 3d5, its L value is equal to 0. S is equal to 5 by 2 because it has 5 unpaired electron, and each unpaired electron has ms value equals to plus half, and therefore S is 5 by 2, and the value of J is equal to L plus S, that is 5 by 2. And on putting these values in equation A, we have G equals to 2. If the value of L for a metal ion is equal to 0, the value of G comes to be 2. In case of lanthanoid and actinoid ions, there is strong LS coupling, and the value of G can be calculated using relationship A, and it differs widely from 2.0023. In the case of lanthanoids and actinoids, there is a strong LS coupling, and the value of G can be calculated using relationship A, and the value of G obtained in this way varies widely from 2.0023. In the case of ionic crystals, the electric fields set up by all the ions may be sufficiently strong to uncouple the electron's orbital momentum from a spin momentum, and thus Russell-Saunders coupling scheme breaks down. Let us see it again. In ionic crystals, the electric fields produced by all the ions may be so strong that it uncouples electrons' orbital momentum from a spin momentum, that is, LS coupling does not take place. Russell-Saunders coupling breaks down. In such cases, on applying magnetic field, the electron spin vector precedes independently about the field direction, and the value of L is immaterial. In such cases, the value of G reverts to 2. In ionic crystals, where LS coupling breaks down due to electric fields produced by ions, the value of G is approximately equal to 2. The intermediate cases may also occur, where L and S are only partially decoupled, not completely decoupled. There is residual orbital contribution to the energy, and the G value is not easily predictable theoretically in such cases. If L and S vectors are decoupled only partially, there is some residual contribution of orbital motion of electron to the net angular momentum, and the G value is not easily predictable theoretically in such cases. And isotropy in the G value. Let us see the term anisotropy. There are two terms, isotropic and anisotropic. if any property has the same value along all the directions in a substance, it is called isotropic. But if any property has different values along different directions in a substance, it is called anisotropic. The G value may be isotropic or anisotropic, as the case may be. In general, the magnitude of G depends on the orientation of molecule containing the unpaired electron with respect to the direction of magnetic field. The value of G depends upon the orientation of molecule containing the unpaired electron with respect to the direction of magnetic field. In gaseous phase or in the solution phase, there is free motion of molecules and the G value is averaged in all the directions. If the free radical is present in gaseous phase or solution phase, it is free to move in all the directions. There is no certain orientation of molecule with respect to the applied magnetic field, and therefore the G value is averaged in all the directions. The average value of G is taken. But in crystals, the motion of molecule is restricted. In a crystal, the molecules cannot perform translational or rotational motion. They can only vibrate about the mean position. If the paramagnetic molecule or ion, that is free radical, is located in a perfectly cubic crystal site, such as octahedral or tetrahedral, G value is independent of orientation of molecule and it is said to be isotropic. If the free radical is present in a perfectly cubic crystal such as octahedral or tetrahedral, the G value has the same value along all the directions, and in this case G value is said to be isotropic. It means if the free radical is present in octahedral or tetrahedral crystal field, the G value is isotropic and it has the same value along all the directions. In the crystal of a lower symmetry, the G value depends on the orientation of crystal with respect to magnetic field and it is said to be anisotropic. If the free radical is present in a crystal of lower symmetry, the G value depends upon the orientation of crystal with respect to applied magnetic field and it is anisotropic. The highest fold rotation axis, that is the principal axis of symmetry of crystal, is regarded as Z axis. The axis with highest order in a crystal is regarded as Z axis and it is called principal axis of symmetry. If Z axis is parallel to external magnetic field, Gz, that is the value of G along Z axis, is called G parallel, that is G value along the Z axis. In a crystal, the axis with highest order is called principal axis of symmetry. and it is regarded as z-axis. And if the z-axis is parallel to the external magnetic field, the value of G along z-axis is called G parallel, which means G value along the z-axis. It is z-axis, x-axis and y-axis. The value of G along z-axis is called Gz. The value of G along x-axis is called Gx, and the value of G along y-axis is called Gy. If z-axis is parallel to applied magnetic field, it is called G parallel, which means G value along the z-axis, because B and Z axis are parallel to each other. In tetragonal site, Gx and Gy are equal and they are called G perpendicular. That is G value perpendicular to the Z axis. It is a tetragonal site in which Z axis is perpendicular to both x and y axis. The value of G along x axis, Gx, is equal to value of G along y axis. Since these two axes are perpendicular to the applied magnetic field, these are called G perpendicular, which means the value of G perpendicular to Z axis. This is G value in perpendicular direction to the Z axis. Both x and y axis are perpendicular to Z axis. Here we have tetragonal crystal with Z axis at theta degree from applied magnetic field. If theta is the angle between the magnetic field and Z axis, the experimental G value is given by the following relationship. If Z axis of a tetragonal crystal is present at an angle theta with respect to applied magnetic field, the value of G is given by the following relationship. G is equal to G parallel square into cos square theta plus G perpendicular square into sin square theta. Here G parallel is G value along Z axis and G perpendicular is G value along perpendicular direction to Z axis. And now the time for self-assessment. Calculate the G value for PR triple plus ion. Here is the solution of this problem. PR triple plus ion has electronic configuration 4f2 5d0 6s2. With the help of box diagram, it can be represented as follows. This is F subcell in which 2 electrons are present, and these are the ml values of these orbitals. L is equal to summation of ml values. The first electron has ml value equals to 3 and the second electron has ml value equals to plus 2, and accordingly capital L will be summation of ml values, that is plus 3 plus 2, and the net result is 5. Capital L is equal to 5. S is equal to summation of ms values, summation of magnetic spin quantum number. This electron has ms value plus half. This electron also has ms value plus half, and their summation will be equal to 1. Capital L is equal to 5 Capital S is equal to 1 and the value of J varies from L plus S, that is 6, to L minus S, that is 4 in integral steps 6, 5 and 4. There are 3 values for J. For F2 subcell is less than half filled. This is less than half filled in the case of 4F2, and hence the lowest value of J is selected for the ground state. Thus, the values of L, S and J for PR triple plus ion are 5, 1 and 4. The value of G is equal to 3 by 2 is given by this relationship. As we have seen earlier, we have already seen that the value of L is 5, S is 1 and J is 4 for PR triple plus ion. On putting these values in this equation, we have this like expression. On solving this term, we have G equals to 3 by 2 minus 28 by 40, and on further simplification we get G equals to 0.8. Thus the G value for PR triple plus ion is 0.8, which is much smaller than that for free electron, that is 2.0023. Thank you for watching the video with concentration. Please like and share it, and if you have not subscribed my channel yet, please subscribe it so that you get information regarding my new videos in time. Thank you again.